In today's video, we're going to cover how to find the domain of a function. Let's say we have a simple linear function like f of x equals 3x plus 5. So when we're looking for the domain, that means that we're looking for the input values, or in this case the x values, since that's our variable, that are allowed in this function. In other words, are there any limitations? So let's look at the function. We have 3 times some number plus 5. So is there any number that we cannot triple and then add 5 to? Usually we like to think of positive or negative numbers, maybe fractions, and also 0. Any of those numbers can be multiplied by 3, and then we can add 5 afterwards, which means in a linear function like this, the domain is going to be all real numbers. We have a couple of ways of writing this. We can use set notation, where we use the braces and write x with a vertical line, which means such that x is a member, using this symbol, of all real numbers. If we were to use interval notation, then the domain would be from negative infinity up to positive infinity. If the function was a quadratic, let's say 2x squared minus 8, then just like the linear equation above, we can look and see that x is being squared, then doubled, and then we're subtracting 8. There's absolutely no limitations to what we can plug in for x, so the domain would be all real numbers. The same is true for a more complex polynomial. Let's say we have 4x cubed plus 7x squared minus 3x plus 10. Again, we're looking for any place where the input value, the x, is, and seeing if there are any numbers that we cannot plug in mathematically. In this case, the domain is, again, all real numbers. Now, the limitations I mentioned will come into play usually in a few scenarios that we need to be aware of. One of which is a denominator. Let's say we had 1 over something. We'll just call it x for now. We know that we cannot divide by 0, so that means whatever was in the denominator, whether it was just x or a longer polynomial, here we know the x, or the denominator, cannot equal 0. Another common scenario is the square root function. Let's say it's square root of x. In this case, we cannot take the square root of a negative number, so whatever the radicand is, the part underneath the square root, must be greater than or equal to 0. If you're working with logarithms, log of x, in this case, you must take the log of a positive number. So whatever we're taking the log of, in this case x, must be greater than 0. One other example to look out for is in real-world situations, for instance distance or time, we cannot have a negative number, so that might also limit the domain. Let's take a look at some examples. Let's start with a rational function. Say we have f of x is equal to 3 minus x over x plus 5. In this case, I like to separate the numerator and denominator to see if they each have limitations. The numerator is just 3 minus x, so we can subtract any number away from 3, and it will work mathematically. Even if we end up with 0 on top, 0 divided by anything except 0 is just 0. So there's no limitations on the numerator. For the denominator, we know that this cannot equal 0, so we're going to set x plus 5 not equal to 0 and solve for x. In this case, that means x cannot equal negative 5. So let's see what that looks like on a number line. If negative 5 is here, we know we cannot equal negative 5, so we're going to use an open circle to indicate that we're not including negative 5, but every other value to the left and right of negative 5 is good, so we can shade on either side. Using set notation, the domain will be x such that x cannot equal negative 5. And with interval notation, the domain goes from the far left, which is negative infinity, up to negative 5, does not include the negative 5, and then up to positive infinity. So it would look like this: negative infinity, comma, negative 5, and then u for union, and we'll continue from negative 5, also parentheses, comma, infinity. If you need a refresher on interval notation, we just put out a video on that topic, and there'll be a link at the end screen as well as in the description. So please check that out after you finish this video. Now, what if our rational function looked like this? F of x equals 2x minus 5 over x squared plus 2x minus 8. We're going to look at the numerator first real fast and notice that we do not have any limitations, so everything up here looks fine. Now, just like before, the denominator we know cannot equal 0, so the first thing we'll do is set that denominator so it cannot equal 0. And now in order to solve this, we're going to have to factor this trinomial to solve for the values that give us a 0. In this case, we're going to need two numbers that multiply to -8 and then add to a +2. So if we break down -8 into its factors, we know that plus or minus 1 can multiply with plus or minus 8, and same with plus or minus 2 with plus or minus 4. Now, since we're multiplying to get a negative number, that means that one number must be positive and the other negative. And since we're adding to a positive number, then the larger of the two numbers must be positive. That means if we took a +8, we would use a -1, but that adds up to 7, not 2. Using 4 and -2, it does multiply to -8, and it adds or combines to get a +2. So the binomials would be x plus 4, since we had a +4, times x, and then the -2 means -2. And this cannot equal 0. Because these binomials are multiplying by each other, if either is equal to 0, then the entire equation would equal 0. So we can set each one to where they're not equal to 0. X plus 4 cannot equal 0, and x minus 2 also cannot equal 0. Therefore, x cannot equal -4, and x cannot equal +2. Let's graph these on a number line to see how this looks. So we'll plot -4 over here and +2 over here. The only limitation is that x cannot equal either of those two numbers, so we're going to use an open circle to indicate we're not including them. But every other number on all sides would be part of the domain. So we're going to shade to the left, in between the two numbers, and to the right. In set notation, we would say the domain is x such that x cannot equal -4, comma, 2. And then for interval notation, notice we have three areas that work: everything to the left of -4, between the two numbers, and to the right of 2. So the domain would be from -infinity up to, our first stopping point is -4. We're not including that, so we need parentheses. U to indicate a union that joins the sets together. We're going to pick back up at -4, also not including, so we use parentheses, -4, comma, 2, close with a parentheses again for the same reason, we're not including 2, and then one more union, and continue from 2 up to +infinity. Now what if our function looked like this? We have f of x is equal to 4x plus 7 over x squared plus 5. Looking at the numerator, we have no limitations on what we can plug in for x. However, with the denominator, again, we need to set that not equal to 0 because we cannot divide by 0. So x squared plus 5 cannot equal 0. Subtracting the 5 to the other side, we get x squared is not equal to -5. So to solve for x, we would normally take the square root of both sides, but we know we cannot take the square root of a negative number without using imaginary numbers. So the lowest value x squared could be would be 0, but then we're adding 5 to that, x squared plus 5, and therefore the denominator will never equal 0. We had no limitations in the numerator or denominator, so the domain is all real numbers from -infinity to +infinity. Now let's take a look at a square root function. Say we have f of x is equal to the square root of x plus 3. The section underneath the square root, the x plus 3, is called the radicand. And just like we saw a minute ago, we cannot square root a negative number. So what that means is that the radicand, x plus 3, must be greater than or equal to 0. It can equal 0 because the square root of 0 is 0. So if we subtract 3, we have x is greater than or equal to -3. On the number line, we can plot -3 here. We'll use a closed circle because it's not just greater than, it's greater than or equal to. And because it's greater than, we'll shade to the right. In set notation, the domain is x such that x is greater than or equal to -3. With interval notation, we're starting at -3 and we're including the -3. So we'll use a bracket, -3, and we're going all the way to +infinity. And we always use parentheses around infinity, whether it's positive or negative. How about this one? We have f of x is equal to the square root of x squared plus x minus 30. We know we cannot square root a negative number, so right away, we're just going to set the radicand, everything inside, to greater than or equal to 0. X squared plus x minus 30 is greater than or equal to 0. Like we did before, we'll need to factor this trinomial. We need factors of -30 that multiply to -30, but also add to a +1. Since it multiplies to a negative, we know one factor must be positive while the other is negative. And because we're adding to just one, that means that the absolute value of the numbers must be close to each other. In other words, if we picked 30 and -1, that would combine to 29. That's way too far apart. So I'm thinking something closer to the middle. Let's try the positive or -5 with the positive or -6. We need the larger one to be positive, which would be the 6, and that would pair with -5 in order to multiply to -30. And then 6 plus -5 is +1. So factored, it looks like this. We have x plus 6 times x minus 5. And we know this must be greater than or equal to 0. Let's set each binomial equal to 0 to see which critical points that we have. So x plus 6 equals 0, and x minus 5 equals 0. In the first case, x would equal -6, and over here, x would equal +5. We'll put this on a number line. -6 here, +5 to the right over here. Now, since we know these two values give us exactly 0, and the inequality allows us to equal 0, right? It's greater than or equal to 0. Then we can start with closed circles at both points. Now what we need to do is test on either side or between the numbers to see if that gives us a positive or negative value. And we're only looking for the positive values since we need to be greater than or equal to the 0. Let's pick any point to the left of -6. That would be in this vicinity here. If we pick, let's say, -10, we can plug that into the binomial here. And the nice thing is we don't actually need to solve the problem. We just need to figure out if it's going to end up being positive or negative. So we'll plug in -10. -10 plus 6 is a negative number, so we have a negative. And then -10 minus 5 is another negative number, which means we have a negative times another negative, which would give us a positive value in this section. Now we need to test any number between -6 and 5, not including those numbers. So 0 is somewhere in between. 0 plus 6 is a positive number. 0 minus 5 is negative. Multiply those two, you would get a negative number. So that's no good. Finally, to the right of 5, we can pick, let's say, 7. 7 plus 6, that's positive. 7 minus 5, also positive. Multiply two positives, we end up with a positive. We're looking for the answer to be greater than or equal to 0. So we're going to shade anywhere that we got a positive result, to the right of 5 and to the left of -6. Set notation looks like this. The domain is x such that x is less than or equal to -6, this area here, comma, and then x is greater than or equal to +5. With interval notation, from left to right, smallest numbers to largest, we're going from -infinity all the way to the left, up until -6, and we have a closed circle. We'll use a bracket to include the -6, U for union, and then we skip this middle section and start up again at 5, including the 5. So we'll open with a bracket, 5, comma, infinity. How about this function? F of x equals 3x plus 8 over the square root of x plus 2. The numerator has no limitations on what we can plug in. And for the denominator, we notice two things. One, we're taking the square root, which usually means that we're going to set the radicand, x plus 2, greater than or equal to 0. However, since we're in the denominator, we cannot equal 0. Instead of x plus 2 is greater than or equal to 0, it can only be x plus 2 is greater than 0. That means that x must be greater than -2. Set notation would be the domain is x such that x is greater than -2. And for interval notation, we're starting at -2, not including, we'll use parentheses, comma, and then up to infinity, parentheses. Here's another good example to look at. F of x is equal to the square root of x minus 3 over x squared minus 81. This time, the numerator does have a limitation since we're using the square root function. So x minus 3 must be greater than or equal to 0 because we're still allowed 0 in the numerator. So that means x must be greater than or equal to 3 so far. But we still have the denominator to take care of. The denominator cannot equal 0, so we'll set x squared minus 81 not equal to 0. There are two methods to solve for x in this case. The first is to add 81 to the other side, so x squared now cannot equal 81, and then take the square root of both sides, keeping in mind that the result is going to be a positive or negative value. In this case, x cannot equal positive or -9. The other method is to recognize that x squared minus 81 is the difference of perfect squares, and we can factor it like this. It would be x plus 9 times x minus 9 cannot equal 0. We would set each of these two to not equal 0, and in the end, we would get x cannot equal positive or negative 9. Now in this case, remember, we have two limitations here. The first one was from the numerator, where x has to be greater than or equal to 3, and from the denominator, where x cannot equal positive or negative 9. Let's plot that out on a number line. Let's put negative 9 here, positive 9 here, and 3 about here. So based on the denominator's limitations, we know that x cannot be positive or negative 9, so let's represent that with the open circles. Now let's look at the numerator. We had x is greater than or equal to 3. Because it's or equal to, that means it's going to be a closed circle. And greater than means we're shading to the right. Again, we can't actually hit 9, so we'll go around it. And for the domain, what we're looking for is the intersection of these two sets. In other words, the numbers have to work for both components, the numerator and the denominator. So if we have x is greater than or equal to 3, that means that anything to the left of 3 is no good. So this is completely out. Everything else lines up. We have greater than or equal to 3, and we're avoiding the positive 9 with an open circle. In set notation, we would have the domain is x such that x is greater than or equal to 3, comma, x cannot equal 9. In interval notation, the smallest number, or farthest to the left we can go, is 3, and it includes 3, so we'll use a bracket, 3, comma, and then our first stopping point is 9. We'll put 9, and we're not including it, so we need a parentheses, union, to connect the sets, and then we'll continue after 9. Open with parentheses again, comma, infinity. Here's another very important example to look at. Say we have f of x is equal to the square root of x plus 4 over the square root of x squared minus 25. The numerator is pretty straightforward. We cannot have a negative here, so x plus 4 must be greater than or equal to 0, and simplifying, x is greater than or equal to negative 4. In the denominator, we have to be careful about two things. The square root means no negatives in the radicand, and being in the denominator means that it cannot equal 0. So we'll set x squared minus 25 greater than 0. This is another difference of perfect squares. It would factor to x plus 5 times x minus 5 greater than 0. So let's start with the critical points, the ones that actually get us equal to 0. In the first binomial, x plus 5 equals 0 means that x equals negative 5. And in the second binomial, x minus 5 equals 0 means x equals positive 5. To make things easier, we're going to use two number lines, one for the numerator and one for the denominator. The numerator was straightforward. We just had negative 4, and x is greater than or equal to, that means it can include the negative 4, and go to the right. For the second number line, let's plot the points as if they were lined up just underneath the first number line. So if negative 4 is here, negative 5 is going to be somewhere to the left, over here, and positive 5 would be over here. Because each of these values equals 0, and we're looking to be greater than 0, first we can put open circles at each point. And then like before, we're going to have to figure out in each of the three sections, to the left of negative 5, in between the two numbers, and to the right of 5, if those give us a positive value, just like we want. Let's choose anything to the left of negative 5. We'll use negative 7. Plugging into the binomials over here, negative 7 plus 5 is a negative number. Negative 7 minus 5 is another negative. Two negatives multiply to positive. So this whole section is positive. Between the two numbers, we'll use 0. 0 plus 5, that's positive. 0 minus 5, negative. Multiplying the two means that all of these numbers here give us a negative value. And then finally, to the right of 5, let's choose 10. 10 plus 5, that's positive. 10 minus 5, also positive. Two positives will multiply to get another positive number. Right now, we have three areas that look like they could work for us. The positive values here, the positive values here, and everything to the right of negative 4 here. Now let's put them all on a single number line to better compare. Negative 5 here, negative 4, and then positive 5. Remember, we're looking for the intersection, and that requires that all the values be true for both of these number lines. On the first one, we have a hard stop at negative 4, which means anything to the left of that is no good. So this section, negative infinity up to negative 4, is no good. Now what's happening between negative 4 and positive 5? On the first number line, everything is good from negative 4, including that number, all the way to the right. However, in the second inequality, we can see that that section where -4 falls into, between -5 and 5, is an area that will not work for us. The only place it can begin is at +5 and to the right. So what that means is everything from -4 to +5 is also completely out. We know +5 was not included. We'll use open circle and shade everything to the right. So notice that this is the intersection of the two above. All of the numbers to the right of 5 are valid in both the inequalities that we solve for. Finally, let's take a look at one last example. Say we have f of x is equal to the square root of x squared minus 9 over the square root of x minus 3. We'll split these up. For the numerator, we know x squared minus 9 must be greater than or equal to 0. We can factor again. That would give us x plus 3 times x minus 3 is greater than or equal to 0. So now we want to find the critical points. What would make this exactly equal to 0? So x plus 3 equals 0, as well as x minus 3 equals 0. And therefore, x would be positive or negative 3. We'll plot just those points on the number line for now. -3, +3. And since it's or equals 2, we'll use a closed circle at both points. And like before, we're going to need to test each of these three sections to see which one gives us a positive value. Let's try -4 in this section. So -4 plus 3, that's a negative. -4 minus 3, that's another negative. Two negatives multiply to a positive. So that section works. Since we're looking to be greater than or equal to 0, in between the numbers, we can pick 0, 0 plus 3, positive, 0 minus 3, negative, multiplies to negative. That's no good. And then let's try +4. 4 plus 3, positive. 4 minus 3, also positive. They multiply to get a positive number. Let's shade the sections that worked. To the left over here and to the right. Now let's solve for the denominator. The square root means we cannot have a negative underneath, and since it's part of the denominator, it cannot equal 0. X minus 3 must be greater than 0, and therefore x must be greater than 3. That number line looks like this. I'll line up the 3's, put it right here. This time it's only greater than, open circle, and to the right. Once more, we need the intersection between these two. Down here, we can clearly see nothing to the left of 3 is going to work, so this is completely out. Everything to the right of 3 is good. However, 3 itself, while it's included up here, we cannot have it in the denominator, otherwise we're dividing by 0. So the intersection of these two would be that x is greater than 3. In set notation, x such that x is greater than 3. And interval notation, starting at 3, not including, 3, infinity. If you'd like a refresher on interval notation, which we covered quite a bit today, please check out this video here that explains all the basics you need to know.